You throw a red ball into the middle of a green lawn. Your dog takes off immediately, tail going wild, nose to the ground, and then stops dead a couple feet short of the ball, circling, sniffing, looking almost right at it without finding it. You're standing there pointing, calling its name, wondering if your dog is messing with you. It finally looks up at you with a face that says, "I genuinely don't know what you're talking about." Meanwhile, you're already halfway to concluding this dog just isn't very bright. It's not messing with you, and it's not dumb either. A lot of us grew up believing dogs see the world in black and white, like they're watching an old silent film. That's not true. This is the story of an eye built for a completely different job than yours, and it starts with a claim nobody ever actually checked. The dogs are totally colorblind idea didn't come out of a lab. It came from a dog training manual published in 1937 by Will Judy, founder of National Dog Week in the US. He wrote that dogs likely only see shades of black and gray. No data, no experiment, just a guess someone put in print. But that guess spread fast, repeated in pet care books and vet clinics for the better part of 50 years. In the 1960s, some primate researchers pushed the idea even further, arguing that only primates, meaning us, could truly perceive color. There had actually been a handful of earlier attempts to test dogs directly, going back decades, but the results were inconsistent enough that nobody built a clear picture out of them. So, when did that picture finally come into focus? In 1989, vision scientists Jay Knights, Timothy Geist, and Gerald Jacobs, working out of the University of California, Santa Barbara, ran a much more rigorous set of experiments. They trained 3 dogs, 2 greyhounds and 1 toy poodle, to make repeated choices between carefully controlled light stimuli, then systematically varied wavelength and brightness to check whether the dogs were actually responding to color, not just to differences in how light or dark something looked. Across thousands of trials, the pattern held. Dogs can tell colors apart, just not the way we assumed. So how does color vision actually work? Light hits the retina, where cells called cones each respond to a different slice of the light spectrum. Normal human eyes have 3 types of cones, tuned to red, green, and blue, and the brain stitches those signals into a full palette. Dogs only have 2. You didn't get that 3rd cone by accident. Your fruit-eating primate ancestors needed to spot a ripe red or orange fruit against a wall of green leaves, something 2-cone vision is bad at, but a stationary, well-lit problem that trichromacy solves nicely. In other words, the eyes you're using to read this were built for picking fruit, not for stalking prey at dusk. That's exactly where the dog's story splits off from ours. Here's the term to hold on to: dichromatic vision. The dog's 2 cone types peak at roughly 429 and 555 nanometers, the blue-violet range and the yellow-green range. No cone catches red at all. Functionally, a dog's color system runs almost exactly like a human with red-green color blindness, a condition affecting roughly 8% of men and 0.5% of women of Northern European descent. Not sees nothing, just missing one of the 3 channels. And dogs aren't alone in this, by the way. Pigs, cattle, squirrels, even some carnivorous bats are dichromats too. Across mammals, it's humans and our close primate relatives who are the odd minority running 3 cone types, not the other way around. Sounds like a pretty settled conclusion, right? But Knight's team had still only tested 3 dogs. Science wants more than one result before it trusts something completely. In 2013, a team at the Russian Academy of Sciences ran a different kind of test on 8 untrained dogs. They set up choices where color and brightness pointed in different directions to see which one the dogs actually relied on. The dogs went with color, consistently. It wasn't a rerun of the 1989 study. It answered a different question, but it landed on the same underlying picture. Color genuinely matters to how a dog reads a scene, dichromatic limits and all. But here's where it gets more interesting. If a dog is basically a red-green colorblind human on 4 legs, why does its world look so much duller than what an actual red-green colorblind person reports seeing? Fair question. This is where the tidy explanation starts to fall apart a little. A dog's retina holds only about 10 to 20% of the cone density found in the center of a human retina. And dogs don't have a fovea either, that dense patch of cones that gives human eyes their pinpoint sharpness. Fewer cones, less concentrated, means even inside the colors dogs can see, blue and yellow, those colors show up paler, less saturated than what you'd see. A tennis ball that looks screaming yellow to you might read as a dull, washed-out yellow to a dog. Worth a quick caveat here. Under very specific, tightly controlled lighting, a few studies have found dogs can occasionally pick up on red versus green cues too, probably by leaning on brightness and contrast rather than color itself. It doesn't undo the dichromatic picture, just a reminder that biology rarely draws as clean a line as a one-sentence claim online. So why did dogs end up with this particular trade-off? One influential idea. Color vision matters most in daylight, close-up, stationary situations. Think foraging fruit. It matters much less at dusk, at a distance, with something moving. Dogs' ancestors hunted hardest at dawn and dusk, when light is low and everything moves fast. In that world, telling red from green is close to useless. What actually keeps you alive is spotting a shapeshift in dark grass and doing it instantly. So instead of building around cones, the dog retina leans hard into rods, the photoreceptors that don't distinguish color but are brutally good at catching dim light and motion. Dogs carry a much higher ratio of rods to cones than humans do. Add in a reflective layer behind the retina called the tapetum lucidum, the same thing that makes a dog's eyes glow eerie green in flash photos, which bounces light back through the photoreceptors a second time before it escapes. Light, motion, darkness. That's the trio a dog's eye is built around. The numbers make the case on their own. A dog can pick out an object moving in a straight line from roughly 900 meters away. A human, under the same conditions, tops out around 580 meters or less. Take the motion away, and that edge mostly disappears. Dogs aren't especially good at spotting something sitting still. They're just exceptional at spotting something that isn't. A dog's eyes also sit further to the sides of the head than ours. How much depends a lot on skull shape, since a long-nosed sighthound and a flat-faced breed see the world quite differently. But on average, that gives a field of view of roughly 240 degrees, compared to about 180 for a human. The trade-off is a narrower zone where both eyes overlap, the part that gives you precise depth perception. Wider view, weaker depth cues, another trade baked into the same pair of eyes. Here's a small, oddly specific detail. Dogs also seem to tolerate faster flicker than we do. A light or screen flashing around 60 times a second reads as steady to a human eye. But under bright conditions, a dog's visual system can still register the flicker up to roughly 75 times a second. Old tube TVs, buttery smooth to you, may well have looked noticeably flickery to the dog curled up next to you on the couch. What about sharpness, though? This is the actual cost. Estimates vary a lot by dog and by testing method, but a commonly cited range puts average canine visual acuity somewhere around 20/50 to 20/75, meaning something you can see clearly from 50 or 75 feet away. A dog may need to close the distance to about 20 feet to see just as well. Its world, even within the colors it can perceive, tends to be a little blurrier than yours, like walking around with a mild, uncorrected prescription. Some breeds do better than others, though the exact numbers per breed are much less well established than the pop science lists suggest. Now go back to the red ball on green grass. Your dog wasn't being clumsy. With only blue and yellow sensitive cones on board, that red ball and that green lawn likely read as close cousins of the same washed-out gray-brown to your dog. The sharp contrast that jumps out at you barely registers for it. The ball doesn't vanish exactly. Brightness, shadow, texture, and of course smell are all still in play. But it loses most of the one cue, color contrast, that made it obvious to you in the first place. Swap that red ball for a blue one, and things usually change fast. Sharper contrast, found in seconds, a lot less standing around confused in the yard. You don't need to retrain the dog. You just need to work with the eyes it actually has. None of what a dog's eyes gave up for red went to waste. Add it up and you've got a real system. Dense rods, a reflective tapetum, a faster flicker threshold, motion detection at roughly 1.5 times human range, a wider field of view, several small adaptations, all pulling toward the same job. Don't miss anything moving through low light. Every time your dog's head snaps toward a falling leaf you haven't even registered yet, that's this system firing, quietly and precisely. Which is also why dogs are so good at catching a frisbee mid-flight, in fading evening light, while you're still squinting to find your keys. It isn't seeing a poorer version of your world, it's seeing a different trade entirely. Less color, less sharpness, but faster, sharper in the dark, built for the exact moment the sun goes down, not for a red ball sitting in the grass at high noon.